be question 3. It says use the SRP table to match the terms below. This is a voltaic cell and you are looking for the most positive potential. Really, eventually you will know that this is a voltaic cell because what makes a voltaic cell is the oxidation takes place in one beaker or one place and the reduction takes place in another place. And the reason we have to have the oxidation and reduction take place in different locations, different beakers in this case, is so that the electrons go through the wire. And that will be happening here as well. And so this question asks, so what was the species oxidized? Number of electrons lost in the oxidation half reaction, the species reduced, and the number of electrons gained in the reduction half reaction. But we have to figure out what those reactions are first. In order to do that, we'll get out our SRP table with reduction half reactions. And a good way to do it is to sort of look at the materials that you have as far as oxidation occurs. Start at the bottom and work your way up until you see something on the product side that you have. So we have zinc solid right here. And zinc solid, if I take this reduction half reaction and flip it to make it an oxidation, I will change the sign and it will be plus 0.76 volts. So let me write that out. Our oxidation will be zinc solid goes to zinc 2 plus 2 electrons, which means that our species oxidized will be zinc solid. The number of electrons lost in the oxidation half reaction, well, that's this number of electrons here. So we have 2 electrons lost. We'll come over to our reduction, and in our reduction side, one way to do it is to start at the very top and see what you have. So for example, we don't have permanganate, we don't have chlorine gas, we don't have oxygen gas. Let's see, what do we have? We don't have bromine. We have Fe3+. No, we don't have Fe3+. I apologize. Can't do this one either. Don't have iodine, don't have copper 2+, don't have hydrogen ions. Blah, 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 blah. We do have Fe2+. So this is the first reduction reaction that we can do. It is minus 0.45 volts. That's negative. That's not like we would love to have. Sorry, I'm off the page there. There we go. So we have Fe2+. It's negative 0.45 volts. That's not that good, but it will still be a voltaic cell. Let me explain that part now. So let me just say this. We're going to do the Fe2+. Plus 2 electrons goes to Fe solid. And now let me zoom back out a bit. That means that Fe2+ will be the species that's reduced. And the number of electrons gained in the reduction half reaction will be 2 for this. Now, again, that's sort of the answer to the question, but the bigger picture here is, well, let's look at the overall process, which is going to take our oxidation and reduction half reactions. So I'm just going to write these 2 reactions down here. So zinc solid going to zinc 2+ plus 2 electrons. From our list, the oxidation potential of that is going to be 0.76 volts. For our reduction half reaction, our reduction half reaction is minus 0.45 volts. If we were to think about what our overall reaction is, first off, the electrons always have to cancel. So the fact that there are 2 electrons produced and there are 2 electrons consumed exactly cancels out. Then our overall reaction will be zinc solid plus iron 2 goes to zinc ion plus iron solid. And when we add reactions like we just did, we add cell potentials or voltages, and 0.76 minus 0.45 is 0.31 volts. And we'll call this our cell potential of 0.31 volts. And we call it our cell potential because the entire thing is called a voltaic cell. And it is the entire thing that is needed to try and power a light bulb. Although with 0.31 volts, it would have to be a pretty tiny light bulb, since most light bulbs require more volts. Okay. Now again, we can imagine that in this picture, we have zinc solid, which is this metal strip right here. It's going to split into 2 electrons and zinc 2 plus. Those electrons are then going to go through the wire, light up the light bulb, well, in theory at least anyway, then keep on going over here where they will meet up with an Fe2 plus. And actually, what's different is since you're making a solid this time, the Fe solid, the iron solid, actually sticks to the Fe solid that's already there. So what you will observe over time as this voltaic cell, as this battery keeps going, is the zinc solid will react away, so there will be less zinc here, and the iron solid will become bigger, bulkier, as the iron solid from the solution deposits on the iron solid that's already there. So that's more or less a full description of this problem. Are there any questions? And I know this is different than the problem you'll get, but it's closely related, and hopefully by watching this video or by doing the homework, you'll be able to do this.